In this video, I'm going to be explaining Mason's rule, but I'm not going to go in depth. I'll make another video where I will explain it in details. I just want to actually introduce it with this particular question. Mason's rule is used to find the transfer function of a block diagram. Like given a block diagram is used to find the transfer function, converting it to this form here. So from Mason's rule, the transfer function of signal flow graph actually is called a signal flow graph after converting it from a block diagram. So you can use Mason's rule to find the transfer function. So Mason's rule states that the transfer function of a signal flow graph is equal to summation of from k equal to 1 down to k equal to n of the forward path gain and then delta is the cofactor of the forward path, all divided by the determinant delta. So tk, let me describe the parameters. T subscript k is equal to the forward path gain while dk is equal to the cofactor of the forward path, path. So now, and d, this actually delta, I'm just calling it d. This delta k, delta subscript k. Delta subscript k. This is also delta, which is the determinant. The determinant is from this determinant that you get the cofactor. So the determinant is 1 minus the sum of all loop gains and plus the sum of gain product. I'm going to explain this like in depth in a video later on, not now actually, but after my next two videos. The next video I'm going to explain it very well, like very well. So I'm just making this video to actually introduce this and solve this question. So it's the determinant is equal to 1 minus sum of all loop gains plus sum of all gain products of all two non-touching loops. So now we have this question which says compute the transfer function C over R output over input of the signal flow graph shown below. So we can see the SFG, the signal flow graph shown below. So we can actually, using Mason's rule, the first thing to find from here is the forward path gain, which is T. So from here we can, the first thing before you find, because for different signal flow graphs you have different number of forward path gains. You can have 1, you can have 2, you can have 3, different numbers, and the determinant is the number of determinants you get is equal to the number of, is also equal to the number of path gains you get. So let's solve. So from here you just check how many paths can we use to get to the output. That's how I actually figure out my forward path gains, the number I have. So from here you can see that we have this path down, and we still have this straight path also down, and we also have this other path, and then down to the output. So there are 3 paths. If you don't understand now, don't bother, I'm just here to solve this question, but I will make a video that will explain it. You understand it very well. So for the forward path gain, we have P1 to be, if you are going through just this, if you are going through this guy just straight down, or let me make my P1 to be different. Let's say you are going through this guy, so that would be G1 times G2 times G3 times G4 times G8. So from here we can see G1 times G2 times G3 times G4 times G8, and then the next we can see from here is this other part that I will use as my P2, G2, G3, G7 and G6. So P2 will be G1, G2, G7 and G6. and then the next, which is P3, will be just the straight path G1, G2, G3, G4, G5 and G6. For the gain, G1, G2, G3, G4, G5 and G6. Now we can continue. The next thing to find is the loop gains. The next thing to find are the loop gains. From the loop gains, you get the determinant, and from the determinant, you can now get the cofactor. So the loop gains will be explained in depth in the video I'm planning to make. This video is just to actually solve these questions. So for loop 1, I'm just going to show you for this one, so that you just have to know the number of loops. A loop is a closed path in a circuit, or for this case is a closed path in this signal flow graph. So we can see that, okay, my L1 is G2, G3. So my L1 is this closed path here, G2, G3, G4, G5, and then coming back down to this point, which is a closed loop, which is a loop. So I've showed you G1, so you can also check the you can also check the signal flow graph for other loops, and you must make sure the loops are complete. If not, your answer will not be correct. So for this question, we have 8 loops, but I'm going to actually teach you in my next, not actually in my next video, but there's a video I'm planning to do that. Minus G5, G6, H1, loop gain, L3 minus G8, H1, L4 minus G7, H2, G minus G7, H2, G2, then L5 minus G4, H4, L6 is minus G1, G2, G3, G4, G5, H3. L7 minus G1, G2, G7, G6, H3. And this is minus G1, G2, G3, G4, G8, H3. This is 3. So now we have the 8 loop gains. We have the 8 loop gains. We can now find the determinant from here. The determinant, there's something else you need to know. From the determinant, let me show you. From the determinant, we also need to find we need to find the sum of all loops. That's the sum of all these loops. Loop gains. Sum of all loop gains. That's the sum of all the loop gains we actually obtained. And then we need to find the sum of all gain products. Sorry, the sum of gain products of all two non-touching loops. So what this basically means is that we need to find two loops that are not touching and then multiply them, and also add as many as that are not, that you multiply that are not touching. So that's what it means. So we need to identify it first. Loop L5 doesn't, you might not understand it now, but in that video I'm planning to make, you will definitely understand it. L4 and it doesn't also touch loop L7. Loop L3 doesn't touch loop L4. Loop 3 doesn't touch loop L4, and all other loops touch. All other loops touch. So now, since we have gotten that we can multiply L5 and L4, just follow me. The determinant, this video is already getting too long. The determinant is summing all the loop gains from the formula using Mason's rule plus L4 plus L5 plus L6 plus L7 plus L8 plus L5 L7 plus L5 L4 L4 plus L3 L4. Now we need to find the cofactor. The cofactor for part 1, that's the forward part gain. Part 1, that's this P1 now, is 1. Is gotten from the determinant. From the determinant, you check the loops that are touching that cofactor part and equate them to 0. That gives you this one. But if you still don't understand, wait for the next, not the next video, wait for the video I'm planning to make. Delta 2 is 1 minus L subscript 5, which is equal to 1 plus G4 H4, and D3 is equal to 1 delta. delta 3. So the transfer function from here, we can get transfer function. Transfer function is equal to C output over input, which is equal to, from that formula, summation k equal to 1 down to k equal to n. N is equal to the number of parts. N is the number of parts. So we have 3 parts, so this will be, and from the formula, I told you tk, but I used p. Yeah, you can use any. T is for transmittance. You can actually use any variable of your choice. I used p, so we can actually use pk here and delta k over delta. So this would be p1 delta 1 plus p2 delta 2 plus p3 delta 3 divided by delta. So substituting the value of delta and also the value of p, you are going to have delta 1 is 1, delta 3 is also 1. So we're going to have this after substituting, even for G2, G3, G4, G5 plus then P2 is G1. This G8, oh sorry, this G8. Yeah, that's G8. So G1, G2, G7 and G6. 1 plus G4, H4 plus G1, G2, G3, G4, G5 and G6. So from here, the determinant is 1. The determinant is 1 minus L1 plus L2. You can still substitute the value of G, like you can substitute the value in form of G, but I'll substitute it in form of L because those values are too long. You can do that one, you can complete it. L5 plus L6 plus L7 plus L8. Then plus sum of all two product of non-touching loops. Plus L3, L4. So this is using Mason's rule. This is your solution. This is your solution. You can go ahead to substitute the value of the value of L1, L2, L3, L4, and so on. Thank you for watching this video. Don't forget to like and subscribe to this channel for more amazing videos like this.